Chapter 8 Motion. A good example is about a railway engine. It is considered to be a good example for motion. In everyday life, we see some objects at rest and other objects in motion. Birds fly, fish swim, blood flows through veins and arteries, cars move, atoms, molecules, planets, stars, and galaxies are all in motion. We often pursue an object to be in motion when its position changes with time. However, there are situations where the motion is inferred through indirect evidences. For example, we infer the motion of air by observing through the indirect evidences. The movement of dust, the movement of leaves and branches of the trees. What causes the phenomena of sunrise, sunset, and changing of seasons? It is due to the motion of the earth. If it is true, why wouldn't we directly perceive the motion of the earth? An object may appear to be moving for one person and stationary for some other. For the passengers in a moving bus, the roadside tree appears to be moving forward. A person standing on the roadside perceives the bus along with the passengers as moving. However, a bus passenger inside the bus sees his fellow passengers to be at rest. What do these observations indicate? Most motions are complex. Some objects may move in straight line, others in a circular path. Some may rotate in a few may vibrate or oscillate. There are many situations involving a combination of this. In this chapter, we will first learn to describe the motion of objects along a straight line. We shall also learn to express such motions through simple equations and graphs later. We shall discuss ways of describing circular motion. We will discuss formula to calculate the motion, speed, acceleration, velocity in this chapter. Types of motion. The main different types of motion here are rectilinear motion or a straight line motion, curvilinear motion, translatory motion or circulatory motion, and oscillatory motions. Examples. Rotation. Fan is an example for rotation. Clock. Pendulum is for oscillating. Piston for reciprocating. Train for linear. Swing machine for a reciprocating. Door for oscillating. Pedaling for rotation. Sawing for reciprocating. Opening and closing of a drawer for reciprocating. Door handle for rotation. So here we clearly explain the different types of motion: straight, curvilinear, translatory, circulatory, oscillatory, and periodic. Describing motion. We describe the location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village is 2 kilometers north of the railway station. we have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We could have also chosen other reference point according to our convenience. Therefore, to describe the position of an object, we need to specify a reference point called origin, and here it is our village is the reference point. Motion along a straight line. The simplest type of motion is the motion along a straight line. We shall learn to describe this by an example. Consider the motion of an object moving along a straight path. The object starts its journey from 0, which is treated as the reference point or the origin. Let A, B, and C represent the position of the object at different instants. At first, the object moves through C and then B and then reaches A, and then it moves back along the same path to reach C through B. Uniform motion and non-uniform motion. Considering an object moving along a straight line, let it travel 5 meters in the first second and 5 more meters in the second, 5 meters in the third, and the 5 meters in the fourth. In this case, the object covers 5 meters per second. As the object covers equal distance in equal intervals of time, it is called as uniform motion. The time interval in this motion shall be small. In our day-to-day life, we come across motions where objects cover unequal distances in equal intervals of time. For an example, when a car is moving in a crowded street or a person is jogging in a park, there are more instances of non-uniform motion. The same is described to you in a graphical way. Uniform motion, a classic example is rotation of the clock, motion of the earth around sun. And for non-uniform motion, the classic example is the car in the traffic. Measuring the rate of motion. Look at the situations given. The bowling speed is 143 h1 in the figure A, and in the textbook it is shown. Please refer the textbook for the figures. What does it mean? What do you understand from the signboard? Different objects may take different amount of time to cover a given distance. Some of them move fast and some move slowly. The rate of which objects move can be different. Also, different objects can move at the same rate. One of the ways of measuring the rate of motion of an object is to find out the distance traveled by the object in a unit time. The quantitative is referred as a speed, and the SI unit of the speed is meter per second, kilometer per hour, etc. This is represented by the symbol ms minus 1 or m over s, m/s. The other units of the speed include centimeter per second and kilometer per hour. To specify the speed of the object, we require only its magnitude. The speed of the object need not be constant. In most cases, the object will be non-uniform. Therefore, we describe the rate of motion of such objects in terms of average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken, that is average speed, is equals to total distance traveled, total time taken of an object travels a distance, and s is in the time and t is referred as its speed v, and v is equals to s over t. Here is a easier way to understand speed. Distance over time. It's another easier way to understand average speed is equals to total distance traveled over total time. Let us understand this by an example. A car travels a distance of 100 kilometers in 2 hours. Its average speed is going to be 50 kilometers per hour. The car might have traveled at 50 kilometers all the time. Sometimes it would have traveled faster, sometimes slower than this. Example, an object 16 meters in 4 seconds and another object 16 meters in 2 seconds. What is the average speed of the object? The total distance traveled by the object 16 meters plus 16 meters is 32 meters. The total time taken is 4 seconds plus 2 seconds is equals to 6 seconds. The average speed is total distance traveled by total time taken is equals to 32 meters. 6x is equals to 5.33 meters per second. Therefore, the average speed of the object is 5.33 meters per second. Speed with direction. The rate of motion of an object can be more comprehensive if we specify its direction of motion along with its speed. The quantity that specifies both these aspects is called velocity. Velocity is the speed of an object moving in a definite direction. The best example for a velocity is the rocket's velocity. Rocket has got a specified speed moving in a specified direction. The velocity of an object can be uniform or variable. It can be changed by changing the object's speed, the direction of the motion, or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of change of motion in terms of average velocity. It is calculated in the same way as we calculate average speed. In case of velocity of the object is changing at a uniform rate, then the average velocity is given by arithmetic mean of the initial velocity and final velocity for a given period of time. That is equals to average velocity is equals to initial velocity plus final velocity. Mathematically, VAV is equals to U plus V, where VAV is the average velocity, U is the initial velocity, V is the final velocity of the object. Speed and velocity have the same units, meter per second, kilometer per hour, etc. The rate of change of velocity. During uniform motion of an object along a straight line, the velocity remains constant with time. In this case, the change in velocity of an object for any time interval is zero. However, in non-uniform motion, velocity varies with time. It has different values at different instants and at different points of the path. Thus, the change in velocity of the object during any time interval is not zero. An example, the odometer of a car reads 2000 km at the starting of the trip, and at the end of the trip we read 2400 km. If the trip took 8 hours, calculate the average speed of the car per hour and meter per second. The solution is distance covered by a car is 2400 minus 2000, that is equals to 400 km. Time lapsed, that is T, is equals to 8 hours. So the average speed of the car VAV is equals to 4 ST, that is equals to 50 kilometer per hour. So to answer such questions, we have to introduce another physical quantity called acceleration, which is a measure of the change in the velocity of an object per time. That is, acceleration is equals to change in velocity for the time taken. If the velocity of an object changes from an initial value u to the final value v in the time t, the acceleration a is v minus u. Acceleration is equals to v minus t over u over t. This kind of motion is also known as acceleration. The acceleration is to be taken to be a positive if it is in the direction of the velocity and negative when it is in the opposite of the direction of the velocity. The SI unit of acceleration is meter per second square. If an object travels in a straight line and its velocity increases or decreases by an equal amount of in equal amounts in equal interval of time, then the acceleration of the object is said to be uniform. The motion of the free falling body is an example of uniformly accelerated motion. On the other hand, an object travels with non-uniform acceleration if its velocity changes at a non-uniform rate. For example, if a car traveling along a straight road increases its speed by unequal amounts in equal intervals of time, then the car is said to be moving with ununiform acceleration. Graphical representation of the motion. Graphs provide a convenient method to present basic information about a variety of events. For example, in the telecast of a one-day cricket, vertical bars are used to show the run rate of the team in each over. As you have studied in mathematics, a straight line graph helps you in solving linear equations having two variables, that is x and y. To describe the motion of an object, we can use line graph. In case of line graphs show more independence, one more physical quantity such as distance or velocity on another quantity such as time. Here, you can just see the x, there is a origin 0, there is a x plus direction, then there is a direction showing y plus. So by using this kind of a graphical representation of two axes, we can represent our graphs. Distance time graphs. The change in the motion of an object with time can be represented on the time graph adopting a convenient scale of choice. In this graph, the time is taken along the x-axis and the distance is taken along the y-axis. The distance time graphs can be employed under various conditions where objects move with uniform speed, non-uniform speed, or remain at rest. A simple example in the graph is shown here. A stationary object, the x-axis remains constant. Then in the uniform velocity, it starts from 0 and you can see a 45-degree line going up. Then in a variable velocity, you can see different curves coming up. Velocity time graphs. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. In this graph, the time is represented along the x-axis. The distance time graph is for a car moving with a non-uniform speed. Here you can see that the graph starts, then the thing stops. Then again for duration, it is shown that it is standing in the same distance. Then again it moves to the next point. It stops for some time. Then again returns to the main bus stop. So this gives a clear understanding that a bus has started from origin, gone to point B at certain speed or distance covered. Then you can see that it has halted for the given time, and again it has accelerated, moved to another position of distance where you can see it has halted for some time and then again taken the return path back to the origin. The other graph also represents velocity versus time, where you can see the clear acceleration of the car and the slowing down of the car. Deceleration of the car is clearly seen in this graph. Equations of motion by graphical method. When an object moves along a straight line with uniform acceleration, it is possible to relate its velocity, acceleration during motion and the distance covered by it in a certain time interval by a set of equations as the equations of motion. There are three such equations. These are V is equals to U plus AT, S is equals to UT plus half AT squared, 2AS is equals to V2 minus U2. Here, U is the initial velocity of the object which moves with uniform acceleration A for a time t. V is the final velocity. S is the distance traveled by the object t. Equation of velocity-time relation. You can see different graphs representing velocity-time relationship. Distance, time, speed and time, acceleration and time, velocity and time. Equation for position and time. Let us consider the object has traveled a distance s in time t under uniform acceleration a. In the distance traveled by the object is obtained by the area enclosed within a velocity time. Position versus time. Uniform circular motion. When the velocity of an object changes, we say that the object is accelerating. The change in the velocity could be due to change in its magnitude or the direction of the motion, or both. Can you think of an example when an object does not change its magnitude of velocity but only the direction of motion? Let us consider an example of motion of a body along a closed path. The given figure here shows the path of an athlete along a rectilinear track. Let us assume that the athlete is running a uniform speed on the straight parts A, B, B, C, C, D, and DA of the track. In order to keep himself on the track, he quickly changes his speed at the corners. How many times will the athlete have to change its direction of motion while he completes one round? It is very clear to know that in a rectangular track, once he has to change his direction of motion. The summary. Here is the summary of what we have learned the last few minutes from chapter 8, motion. Motion is a change of position. It can be described in terms of the distance moved or displacement. The motion of an object could be uniform or non-uniform, depending on whether its velocity is constant or changing. The speed of an object is the distance covered per unit time, and the velocity is the displacement per unit time. The acceleration of an object is the change in velocity per unit time. Uniform and non-uniform motions of the objects can be shown through graphs. The motion of the object moving at uniform acceleration can be described with the help of three equations given below. V is equals to u plus at, s is equals to ut plus half at squared, 2as is equals to v2 minus u2. And if an object moves in a circular path with uniform speed, then it is called as a motion is uniform circular speed. The example is tying a stone on the thread and rotating over your head. And here are the exercises which the children should do at their home. And in case they have to have any doubts, can come back onto the feedback of the chapter. And you can also put this up on your comment section. And in most of the exercises, we will be applying the same formulas what we have understood till now. The main thing what we have understood is about the displacement, velocity, speed, acceleration, uniform speed, uniform acceleration, uniform velocity. Then we cover uniform circular motions, etc. And also we have understood how to plot simple graphs on different velocity, time, velocity and distance, etc. So with this, we will be moving to the end of the chapter. Please complete the exercises at home. See you later in the next chapter. Thank you.